Let's continue with our lecture on analysis of flanged beams. In our previous lecture, we started with the concept and dealt in detail about what are flanged beams, where they may be present in our structures, and we saw different concepts before going into the analysis part. And there, at the end of previous lecture, we discussed 4 cases. And today, we will discuss the analysis of these beams for these 4 different cases. The first case is the one in which the neutral axis lies in the flange of our beam. As we discussed, if we suppose that this is our T-beam here, then this shaded part is known as the flange, and then this part below, we call this the wave. So the first case is in which the neutral axis is in the flange. As we discussed in our last lecture, if the neutral axis is in the flange, then only the area of this concrete or this volume of concrete above the neutral axis, this resists the compressive forces, and this concrete below the neutral axis, we can ignore the volume of this concrete. Since we consider that the concrete does not take any tension forces, we can ignore the volume of the concrete below the neutral axis, and this will be just our normal rectangular beam with width BF and the effective depth is D. And the remaining 3 cases we discuss the conditions in which the neutral axis is in the wave. So these 3 cases are neutral axis is in the wave and the section is balanced, neutral axis is in the wave and the section is under reinforced, neutral axis is in the wave and the section is over reinforced. So let us discuss these 4 different cases one by one. For all these cases, you can see a diagram to the right of each slide, and then we have the discussions on the left side here. The first case is the one in which the neutral axis is in the flange. That means you can see here we have a neutral axis which is represented by this line here, and this neutral axis lies in the flange of our T-beam here. So what we can say is that, as we just discussed, we can consider such beams as a normal rectangular beam of width BF and effective depth D. Since we do not need to consider the concrete below the neutral axis in which the tension forces are acting, we simply consider this a normal rectangular beam with width BF and the effective depth is D here. So all the equations that we have discussed in this lesson till now, the equations for singly and doubly reinforced beams are applicable to this case here. So if you want to find the depth of neutral axis, you can use this formula here, xu by d equals to 0.87 Fy AST over 0.36 FCK BFD. Now B becomes BF here. BF, as we discussed in our last lecture, is the effective width of flange. And then after determining the value of xu by d to find the nominal moment of resistance Mn, you can use this formula here. We also have already discussed the formula, this same formula also. And to determine whether your beam is under reinforced, you can determine the limiting value of xu by d. And if the value of xu that you calculate from here is less than the limiting value, you can call the T-beam to be under reinforced. If the beam comes out to be over reinforced, then you have to redesign the beam. So for under reinforced, you can check this condition also. So this is the simplest case for T-beams. Now if we go to our second case, the neutral axis is in the wave and the section is balanced. Balanced means the value of xu is equal to the value of xu max or xu limiting, but this xu is greater than df. That means xu greater than df implies that this neutral axis lies outside the flange section. So if this is the df that we have here, then the value of our xu is greater than df, so that our neutral axis lies somewhere in the wave. So in this diagram here, our neutral axis is here, as you can see. So for this case, for the case where neutral axis is in the wave and the section is balanced, there are further 2 cases. The first case is when the value of df by d is less than or equal to 0.2, and another case is where df by d is greater than 0.2. So you should remember what we discussed in our last lecture. There we discussed that if this concrete fiber where the strain is 0.002, if we suppose the depth of this concrete fiber from this top of our T-beam to be at a depth of h, then the ratio of h by d for all grades of steel is almost equal to 0.2. This was one value that we derived in our previous lecture. That means if h equals to 0.2d, then we get the value of the depth of this concrete fiber where the strain is 0.002. Now what happens if df by d is less than or equal to 0.2? This means the value of df is less than or equal to 0.2d. So 0.2d is h, that means the value of df is less than or equal to h. So in this case what happens is that if the value of df is equal to h, then our concrete fiber where the strain is 0.002, this lies exactly at this intersection here, the intersection of this flange and the wave. And if df is less than h, then it means that this depth, h depth, lies somewhere below this 1-1 section. So this 1-1 section represents where df equals to h, and this another here, let me say this 2-2 section, this represents where df is less than h, since h is measured from here now. Wherever this section may be either 1-1 or 2-2, you can see that as we discussed in our previous lecture, above this strain level of 0.002, wherever it may be either 1-1 or 2-2, above this level of 0.002, the concrete will be under a constant stress of 0.446 FCK. You can see here the stress diagram also. If this represents the level where the strain is 0.002, then the stress above this strain value is a constant stress of 0.446 or 0.45 FCK. This we also derived from the stress strain curve of our concrete. Here we have 0.002 and here we have 0.0035. So now we can say that our flange will be under a constant stress of 0.45 FCK. So now what we can do is, now we can split this section into two parts here. We will split it in this way. First we will consider a rectangular wave. We will consider this whole section here. We will consider a rectangular wave of width BW and effective depth D is same here. This will be our one section. And then we will consider another section of flange, this section and this section, the remaining part of this T-beam, whose width is now given by this total width. This total width is now given by effective depth BF minus the width of our wave BW. So we will divide our T section in this manner here, and then we will calculate the compressive and tensile forces. So after dividing this section into these two parts, you can calculate the total compressive force by summing these two forces here. First, the compressive force of rectangular beam of width BW and depth D, that means the compressive force of this green area, and then the compressive force of this blue area here. So the total compressive force of the green area is given by this formula here, as we have already discussed: 0.36 FCK BW XU max. BW is now the breadth of the wave, and XU max, because ours is a balanced section, so XU is equal to XU max. This is the compressive force of your wave portion. And now the compressive force of your flange portion, that means this blue area will be this here: 0.45 FCK. The width of that area is BF minus BW, and the depth of your flange is DF. Why 0.45 FCK? Because as we discussed previously, because of this position of our 0.002 concrete fiber, our flanges will be under a constant compressive stress of 0.45 FCK. So in this way, you calculate the total compressive force by summing these two forces. The total tensile force is given by 0.87 Fy AST. And now to calculate the moment of resistance, you need to determine the lever arm. The lever arm for your wave part is given by D minus 0.42 XU max. This formula we have already derived and we know how it came. And for flange portion, the lever arm is given by D minus 0.5 DF. Why? Because lever arm is the distance between the line of action of compressive and tensile forces. For this flange portion, your total compressive force will act at the center of this depth here. That means at a distance of df by 2. So the distance or the lever arm will be d minus df by 2. Now the total moment is given by total compressive force into lever arm. So for the first part of this force, lever arm is here, and for the second part of this force, lever arm is this. So this gives us total moment of resistance. If you take d common here and divide it by XU max by d, XU max by d, then you will get this formula here, which is also given in our clause G 2.2 of IS 456-2000. So these formula are the same here. So in this way, you can calculate the moment of resistance of your flanged beam when the neutral axis is in the wave and the section is balanced for the first case. df by d is less than or equal to 0.2. So once you understand this, for third and fourth cases, it will be easier to understand there also. Let us go to second case of this case 2 here. That is case 2b, where df by d is greater than 0.2. That means df is greater than 0.2d, and we know 0.2d means yachts, so df is greater than yachts. So this df is greater than yachts means that concrete fiber which has the strain of 0.002, that lies somewhere inside the depth of this flange portion. df greater than yachts means yachts is less than df, so yachts should lie within the df. So this is our total depth of our flange section. Our yachts lies somewhere inside this flange section, but we don't know where. So now in the previous case, where you said that the whole of the flange will be under a compressive stress, constant compressive stress of 0.45 FCK, you cannot say this now here, because look at this stress value here. Let me overlap our flange portion on our stress diagram here and show you. This is our flange portion, and this is our level of yachts here. Now you can see that this constant stress line is only applicable to the upper portion. That means your whole flange portion is now not under a constant compressive stress, only some part of it. So let us say that this line of 0.002 strain is at a distance of YF from the top portion here. And that YF you can get by using this formula here. We are not going to derive how this value for YF came. If you look at any standard textbook, you can get this value, but for now we will just use this value of YF here. which is given by 0.15 XU max plus 0.65 DF, but not greater than DF. So if this value is less than DF, then use this value, or if it comes out to be greater than DF, use the value of DF here. So YF is derived using this formula. Now to find the total compressive and total tensile forces, you just have to replace wherever you used DF in your previous slide, that is in our case 2A, replace that DF by YF. So our total compressive stress, now this is our total compressive stress for the wave portion, and for flange portion, instead of DF here, replace it by using YF. Similarly, now the lever arm for the first part of this compressive force will be D minus 0.42 XU max, and for the second part will be D minus 0.5 YF, and multiplying the corresponding compressive forces with their lever arm, and then adding those two compressive forces, you will get the total moment of resistance. So in our previous case, what we did was we divided our T-beam into one flange portion and another wave portion. But now in this case 2B, what actually happens when using this formula is we are dividing this in this way. So this is our flange portion, this is our flange portion, and the remaining is our wave portion. Now only this part and this part compressive forces is given by this formula, and the remaining compressive force is given by this formula here. So remember, we are still using XU max because we are considering a balanced section for this case 2. So case 2 is complete. Now let us go to case 3 here. In case 3, neutral axis is in the wave still, but now the section is under reinforced. That means our value of XU is less than the value of XU max, but still our value of XU is greater than DF. So XU greater than DF means our neutral axis is in the wave, and XU less than XU max means the section is under reinforced. Now case 3 is also similar to how we proceeded in case 2, except that in case 2 we checked for whether DF by D was less than or equal to 0.2 for case 2A, and for case 2B we checked if DF by D was greater than 2, and we derived the formula for these two cases. But now we are not going to use this 0.2, but instead our 3A case will be DF by D is less than or equal to 0.43, and our 3B case will be DF by D is greater than 0.43. So why this? If you remember, when we derived our formula for H by D, when we got the value to be 0.20, actually what was our derivation was that we actually got the value of H by D to be, sorry, let me go back to that lecture here. Not H by D, we actually got the value of H by XU to be 0.43. And we considered that XU is equal to XU max, that is for a balanced section. And then we converted this value of XU in terms of D, and we got the value of H to be nearly equal to 0.2 D here. But since now we have a under reinforced section, we cannot use this formula XU equals to XU max, so we will consider that H by XU is equal to 0.43 here. So H by XU equals to 0.43. That means H equals to 0.43 XU. So if we consider in this first case, DF is either less than or equal to 0.43 D. Then, as we discussed during our 2a case, that means that since df is less than 0.43 XU, now this entire flange will be under a constant compressive stress of 0.45 FCK. Because this 0.43 D is the line where our strain level is 0.0002, and if the value of the thickness of our flange is less than 0.43 D, as we discussed during our last lecture, we can consider this a thin flange section, and whole of this flange will be under a constant compressive stress of 0.45 FCK. So proceed in a similar way as for case 2a, then you can find the total compressive force will be the same, and total compressive force due to flange and wave will be the same, except that in case 2 we used XU max here, but now for this under reinforced section we have to first calculate XU and then use that XU value here. Total tensile force is the same, is given by the steel in this section, and then we multiply the total compressive force with their respective lever arm to get the value of moment here. So this is the similar case as for 2a and also for 2b. Now when df by d is greater than 0.43, only a part of the flange will be under constant compressive stress. So in that case, you have to determine the value of F as we did for our case 2b here. Use the same formula here, except XU for XU max. Calculate the total compressive and total tensile forces. Replace df by yf here now. Replace df by yf. Multiply the compressive forces with their respective lever arm and calculate the value of moment of resistance. So this completes case 3 also, and finally case 4 is the case where the section is over reinforced. That means the value of XU is greater than the value of XU max. This is not a desirable case. We always want to restrict our value of XU to XU max because we do not want over reinforced beam. In over reinforced beam, if you remember, concrete failure will occur first, and concrete failure is brittle failure. It will not give us any warning, and that failure is sudden. So we do not want to design a section which prevents steel failure. So it is therefore recommended either to redesign or to go for doubly reinforced flanged beam than designing over reinforced flange beam. So the case is the same here. For over reinforced we will not be discussing in detail because we do not want an over reinforced section. So remember all the cases that we discussed today from case 1 to case 4 we discussed for singly reinforced T-beams or singly reinforced flanged beams. If we have a doubly reinforced, if we have to analyze or design a doubly reinforced flange beam, then many other things you have to determine as we discussed during our doubly reinforced lectures: MU limiting, MU2, AST1, AST2, ASC, and all these things. The determination of all these things is not much different from what we did during the design and analysis of our isolated over doubly reinforced beams. So we will look at these things when we are doing numericals regarding the analysis and design of flange beams also. We will not have a separate lecture for determination of these things for our flanged beams. So this brings us to the end of our analysis of flanged beam portions. Next 2 or 3 lectures we will have tutorial class where we will deal with the analysis type problems and design type problems for our flanged beams. And then finally, after such many lectures, we will complete the 3rd chapter, which is the design of beams in flexure. And after completing the tutorial classes, we will begin with the design of beams for shear forces. So we will meet again soon in our next class, which will be a numerical class. Till then, stay safe and thank you.